Hello and welcome back everyone. This video is going to cover about this third subtopic of number theory, which is checking of prime numbers. That is whether a given number is prime or not. So what is a prime number? Prime number is any number which is a factor of itself. That means given a number, so first understand the concept of factor. Let's say the number is 15. It can be written like 1 times, 3 times, 5 times, right? So this becomes the factors of a number 15. And let's say 24. This can be written like 1 times, 2 times, 2 power 3 times 3. So these are the factors. Factors of 24 are 1, 2, 3, 4, 6, 12, 24, 8. So these are the factors. And now to check whether this number is a prime number or not. So the definition of prime number says that a number is prime when it's a factor of itself. That means for a prime number, value of so the factors will be 1 and the number itself. So that is the idea of prime number. Now take an example of 7. So the factors are 1 and 7. So this becomes a prime number. But consider the same example of 15, where the factors are 1, 3 and 5. The factors are not 1 and n, which is 15. Hence 15 is not a prime number. Pseudocode for finding whether a given number is prime or not. For that, one needs to figure out the factors of the given number n. And let's say a function is defined. Is prime is a Boolean function. If the number is prime, it will return 1 or true. If the number is not prime, it will return 0. Consider n as the parameter being passed to this function. And here the assumption is made that n equal to 1 is not a prime number. And for that, if n equal to 1, then return 0 or return false. For n greater than 1, one needs to check whether the number has other factors or not. For that, one needs to store the result of factors. So that is being stored in a variable which is initialized to 0 for store factors of a given number. Then a loop will be executed for I starting from 2 to n, do if n mod I is 0, then return false, or let's say increment factor, because it has some factors by 1 unit. So factors now will be updated like factor plus 1. This is step 4, this is step 5, step 6. Seventh instruction will be to check. This is end if factors is greater than 2, return false. Else return true. Because for prime number to exist, there are two factors, one and the number itself. Let us figure out the time complexity for the pseudocode. First instruction will be executed in big O of 1. For remaining instruction, each time factors has to be checked, and this will be executed till the number n. So this will become big O of n, and remaining instructions will be carried in big O of 1. Any efficient way of checking whether a number is prime or not? Yes, there exists a method, and the idea is simple. To understand the idea, consider an example of 64 as the number and list out the factors of 64. So the factors of 64 would be 1, 2, 4, 8, 16, 32 and 64. And from this one can make an observation that 1 times 64 is 64, 2 times 32 is 64, 4 times 16 is 64, and here 8, which is multiplied by itself to get 64. Now, why is this idea being discussed? Because if one can identify whether either of the pair, like from 1, 64, if one can say that 1 is the factor, then 64 automatically becomes the factor. And similarly, if 2 is the factor, then 32 will automatically becomes the factor. And similarly for 8, if 8 is the factor, then another 8 will be the factor. So this idea can be explored, and this will make the solution more efficient for checking the prime numbers. So here let us consider another example of, let's say, n having the value of 57. Here the factors would be 1, 3, 19 and 57. So from here one can see the pairs are 157 and 3, 19. So in 2 iteration one can figure out the pairs, and here maximum of 4 iterations will be required to figure out whether a number is prime or not. Here it will take like 164, 232, 416, 8, 8. So maximum of 4 iteration. Here maximum of 2 iteration. And when checking from 1 to 64 in the previous approach, it was going to take 63 iterations. But here maximum it will take 4 and times 2, 8 iterations. Here 2 times 2, 4 iteration. Just 4 iteration will work out the solution, which is nothing but, if look carefully, the root. So from this one can make an observation that any number, let's say n, and if factor is there, so automatically another pair will exist. So let's say this pair is x, so another pair will be n minus of, or n by x. This would be another. Time complexity for the efficient approach is, the first statement will be executed in big O of 1, and while loop will be executed in big O of n square root of n. Why? Because I square would be less than or equal to n, and I will be less than equal to root of n. Hence that will be the big O of square root of n, and the return statement, return true, would be executed in big O of 1. Hence the time complexity to figure out whether a given number is prime or not using efficient approach is big O of square root of n. Now, given that one has checked a number is prime or not, but the questions can be asked in such a way that figure out or list out the prime numbers within a range. So is there any way to figure out the prime numbers within this range? Yes, and that will be the idea which will be covered in the next lecture. In case of any query or feedback, kindly post in the comment box. Hope you enjoyed the analysis. Thanks for watching.